So if we think about the purpose of a lens, the main purpose of it is to collect more light than your eye would get ordinarily. So let's say we have a point source far away, only a small number of light rays, represented by these two blue ones, will actually hit your pupil. Nearby rays will hit the top of your head or your chin, the red ones. Uh, we could use what we know about refraction to bend these rays back down towards your eye. So we know that if we put prisms here, the light rays going up would get bent back down towards your eye. The problem is we need for all the light that leaves the point source at one time to reach your eye at the same time. In this case, the blue light has a shorter path and there's no glass in its way, so it's going to get there noticeably faster than the red light that has a long path and then is slowed down by glass. There's no way to speed up the red rays, but what we can do is slow down the blue rays. Now, we just want to slow them down. We don't want to bend them. So what we do is use like a piece of window glass. It's essentially flat here so that there's no curvature going straight through the center of the lens. That'll slow them down but not bend them. For rays that lie in between the blue and the red, we'd have to do a little bit of slowing and a little bit of bending. And when we do the math and figure out what shape we need, we actually get this, which is a double convex lens. This is a converging lens because it makes this light come down to a point. Remember, for the mirror, concave was converging, but for the lens, convex is converging, and you just got to remember that, unfortunately. Again, if we assume that we're cutting the surfaces of lenses from spheres, we're going to see a lot of connections between optics with these thin lenses and optics with mirrors. So again, we're going to define focal length as the point where the lens brings parallel light to a focus. In that case, a converging lens has f greater than 0 and a diverging lens has f less than 0. That's the same for both mirrors and lenses. If they're converging, it's positive, diverging is negative. For example, diverging lens here, this is double concave. If we send parallel light through this, what will happen is the light will spread out. And as before, your eye will track back along these lines and say, oh, all the light came from here. That's our focal length. It's one focal length away from the center of the lens. Let's do some examples and see how much this is like what we just saw with mirrors. Let's say we have a converging lens with f equals 0.5 meters, and notice it's positive. An object that's 1.5 meters away from it will give us an image at a location, di, determined by the same thin lens equation. So again, we have this, like we had with the mirror. We solve for di, we get 0.75 meters. That means it's a real image because it's positive. Magnification, we do negative di over do, we get negative 0.5, so it's upside down. The fact that it's between 0 and 1 tells us it is smaller than the object. Now, the difference here compared to mirrors is a virtual image is on the same side of the lens as the object, where it's on the opposite side for a mirror. If we move the object in closer, let's move it to 0.75 meters. Now di is 1.5 meters, still a real image, and our magnification is negative 2. So now the image is larger than the object, but still upside down. Let's move into 0.5 meters. Again, 0.5 for focal length, 0.5 for image distance. There's nothing left for this. 1 over di has to be 0. So di goes to infinity. There is no image. Parallel light leaves the lens. So again, good design for a flashlight. We continue to move closer. Now we're inside the focal length at 0.25 meters. Our image distance is now negative 0.5 meters, so it's a virtual image. Our magnification, negative of a negative, we get plus 2. So the image that we see now is upright and larger than the object. So for a converging lens, what this means is the light is spreading out too fast and too rapidly for the lens to bring it back down to a point. When the light leaves the lens, it's still spreading out. Not as much as it would have without the lens, but it's still spreading out. You could see how this works with this screen capture from the PhET website. You'll do some PhET labs this semester. This is a program at University of Colorado. They have these Java physics simulations. In this case, we have a double convex lens. The X's here represent the focus points, the focal points one focal length away from the lens. When we move the object here, the little thing, inside the focal length, notice the light spreading out from it is still spreading out after it leaves the lens. Not as much, but it's still spreading. Your eye tracks backwards along there and says, okay, that's where the point of the pencil really is. If you do that all along here, you'll get a bigger image than your object. So this is kind of an easy way to visualize it. If you want to go play around with this, it's fet.colorado.edu, and you can just look for all kinds of different simulations.